So with the ultraviolet and visible spectrometer on LADEE, we were able to track the variation of sodium and potassium in the exosphere of the moons from about the same vantage point above the subsoil point for about 5 months. This demonstrated two types of trends: a monthly variation in both sodium and potassium, repeatable variation. We also, though, show episodic variation, such as the enhancement of this metal species during meteor showers, most clearly during Geminids. And so today, I would like to talk about a different kind of variation, which is variation in solar wind input. And we'll concentrate on a couple of events on which we had really large enhancements in the solar wind alpha to proton ratio and overall flux. These are times when we expect the sputtering source to become a considerable source for the atmosphere. Now, before I proceed with that, as I said, meteor showers are the other delta function here, where you increase the source input to the atmosphere in a significant way over a short time scale. And what came out of a very good correlation that Jamie Soleil led between the LDEX measurements and the UVS measurements of potassium was that, okay, we saw this rapid increase in the exospheric profile for potassium, but which coincided with the peak of the Gemini shower. But then after the turn off of the shower, basically, which is shown by the LDEX counts over here, you could see the atmosphere persist for about 4 days before it returned to the half the content during its peak. So from that, you infer a lifetime of about 4 days, give or take, of the exospheric ejecta. And what impressed me was how short this is. This is definitely too short for photoionization to do this. So my conclusion from that was we're losing these adsorbates to the ground somehow. So this is a key point that enables the following work now. So what did we expect about large solar wind events? So this is a simulation. This is supposed to be a movie. Can you play the movie, please? So when a solar wind comes in and you have a large enhancement in plasma and alpha to proton ratio, we expect this sort of brightening of the atmosphere as seen here. And eventually, this is a really broad event for several days, it looks like. And so eventually, the atmosphere, after the passage of the CME, goes back to the original shape. So, a clear brightening in the simulation. This was sodium. The simulation basically had a 30% alpha to proton ratio, about a 10-fold enhancement in solar wind flux above background levels, and several heavies too. So we did get similar, actually, 2 similar events to that sort of event during the LADEE period of performance. One double event in February, and one almost towards the end of the mission in April. And so what's shown here is in blue, this is the alpha to proton ratio as inferred from Artemis. And for the April event, you see for consistently, these are 4 days worth of data shown here. So for about almost 2 days, we get increased alpha to proton ratio about 15% or so. And at the same time, we have high proton flux of about 2 times 10 to the 9, 5-6 times above average. How did the exosphere respond? Well, this is potassium. And well, somewhat strangely, not only do we not see an increase in the atmosphere, but one might say that we see somewhat of a dimming by about 25%. Sodium is a little bit, more complex. maybe you can see an increase. Of course, the complication on all of this is there is as I said, the monthly trend, the repeatable trend, which is a function of composition, micrometeoroid input, which complicates the interpretation a little bit. Now, the other event, the earlier event, let me say that large increases in the helium content of the atmosphere were observed by the LADEE NMS during both of these events. So these are really veritable increases in the alpha to proton ratio. In February, we saw basically a double event for about a day. The alpha to proton ratio went up to 10%, and then the following day, we had an even larger enhancement. So what's really neat about this, and the response of the atmosphere is a little bit more mixed and maybe a little bit more expected this time. It looks like potassium sort of, you can see some sort of enhancement maybe by up to 25% in the latter part of the storm, and sodium is complex. What is significant about these events is these are really wide. Look at the cadence of LADEE UVS. Basically, we have one sample per day, maybe two. So it's easy to miss spiky conditions. But when you have 2 days worth of consistent, blowing of the solar wind, we do expect to catch the, the spatter detect, the spatter vapor. So, to me, what this is one way to see the data. Okay, let's subtract the lunar phase trend from the April event, and it does look like even when you take out the systematic trend, which again has to do with the creep soils, there was a sort of a decrease by about 25% in the first event. Now, when you look at both events and all data at that lunar phase, again, you see that for both of those storms, the atmosphere appears to be overall below the levels that were measured at the same lunar phase in previous months. So all this is, evidence, circumstantial maybe, that something strange is going on. So to me, what really started getting my attention is, okay, the first test should be what are the sputtered rates, and should we see a brightening? And so, for instance, these are the data, and from the measured abundance of potassium here, you can infer an instantaneous source rate of the pre-existing atmosphere. And that's about 4 to 5 times 10 to the 4 potassium atoms per square centimeter in second. So this is now the full Artemis flux convolved with the protons. You see that you go up to 2 times 10 to the 9. And when I did some numbers here with yield, assuming yield of 2%, sputtering yield, for nominal alpha to proton ratio and adjusting for the prevailing alpha to proton ratio during the event, I estimated that the instantaneous sputtering rate should be about 2 times 10 to the 4. So it's not a big increase over the background atmosphere, maybe a 40% increase. But the solar wind isn't just sputtering stuff. And so this is shown here in this green line. So this is the convolution of basically the sputtering profile with a lifetime in the corona of about 10 hours, which is the photoionization lifetime. And so this clearly shows that, somewhere on day 2, we should have been seeing some sort of increase, marginal maybe, but, measurable. Now, the second thing that the solar wind is, it's producing fresh sodium and potassium atoms that stay in the regolith. And the reason we know this is when we make measurements in the laboratory of sputter yields, the yields decrease to about 1/3 when you have a porous surface over a flat surface. So essentially, 2 out of 3 atoms that are produced during sputtering stay in the soil. And they become the so-called ion-enhanced diffusion source. These are now free metals that can diffuse, get to the light, and get photodesorbed again. So when you convolve that portion of the expected atoms in the subsoil, you should be getting almost a factor of 2 increase, a day or so later into the event. And none of this was seen. So my conclusion from this is that the sink rates cannot be constant. In other words, that the solar wind not only is a source for the atmosphere, but it's also a sink. So I spent some time trying to think about how would the solar wind decrease the atmosphere. So one could be via adsorbate spattering. So the increased influx to the surface just spatters the adsorbates out. It turns out those rates are not sufficient. Recoil implantation, pushing things further in, has an even smaller cross-section. Charge exchange, not sufficient for potassium. So the one scheme that I found that works is the following. I mean, basically we assume for a lot of these metals that when they come back to the surface, they stick, they react, we lose them. But for the first time, I believe I actually calculated how long this would take, making some reasonable assumptions about the binding energies and assuming something about the migration energy due to diffusion. So it turns out that if you add fresh oxygen and potassium on these lunar soils, depending on these microphysical properties and how you assume them, you would have to assume that the oxygen is pretty mobile. You get something like 12 hours between potassium finding an oxygen on a grain. So this is quite short, in fact. But you see here in the middle of the CME, you would produce a substantial reduction in the potassium reservoir. So when I put this simple two species ODE, prescribe it, the solution from the ODE solver, prescribe it into a Monte Carlo model, time-dependent Monte Carlo model of the atmosphere. I produce here's the data, and we're trying to reproduce here this dip seen during the event. And sure enough, these are 4 different models. I just varied the photo desorption rate by a factor of 5 and the sink rate by a factor of 2. It turns out you can reproduce the dip approximately seen there if you reduce the sink rates I was showing before by a factor of 5 or so. So if you actually, furthermore, what this solution does, the concept at least, if you estimate now the sink rate during the quiet times when the moon is in the magnetosphere, the sink rate that you would get from that is about 5.5 days, which is basically comparable to what we saw in Geminids. So I think this type of approach, I mean, something evidently eliminates these adsorbates way too soon. We don't lose them in the air, we don't lose them to the solar wind. We have to lose them to the subsurface. We saw this during Geminids, and that was difficult to explain. It seems like, at least occasionally, we see the same during a CME. Instead of a clear brightening, we see initially some sort of dimming of the atmosphere, as if the solar wind is enhancing the sinks. And the only way that I can think of to do this is by introducing fresh metals, reactants, oxygen, and other metals that eat away the existing atmosphere, the reservoir for the atmosphere from previous ejections. It looks like in this simple macroscopic rate model, this can take place within a couple days during a major CME. And this is a simplification. I can see lots of ways that the solar wind can be both a source and a sink. But essentially, these free atoms are provided both by micrometeoroids and by the solar wind. And you can increase the sinks during a meteor shower, for that matter, because there's additional free metals in the soil. So I think that's the take-home message. This diffusion-mediated reactions, there's a finite time. Desorption takes a finite time. Any reasonable photodesorption cross-section, an adsorbate will sit on the grain for a day or two before the next hop. So there's a finite chance as it migrates that it finds the reactants, the oxygens, and it gets lost without getting re-emitted. So that's my main message here.
All right, very good. We have time for a couple questions. Rosemary, I figured you'd have something to say about this.
I do. The problem is if you'll read my Advances in Space Research paper that has just been published, the sputtered sodium and potassium at the moon is escaping. And the reason that your density decreases at LADEE orbit is because the scale height is extremely enhanced. So your sodium is way above where you're measuring. And what your loss is lost to space, and you can you can easily calculate that.
No, the line of sight that I draw, I mean, and LADEE observes is all the way to infinity.
But
So it would
Menelaos,
sample, yes,
the
it is pointing
atoms are
down.
lost to space, they're not lost to the surface. You can easily calculate that.
Yeah, that is included here, Rosemary.
But you know, it's not.
Here's
it's
what
not
we
being
should see.
sequestered at the surface.
This is what we should see, this type of profile. But you are referring to a different thing. As I said, 1 out of 3 atoms escapes to the exosphere, and that's the portion that we may or may not see. The other 2 atoms remain in the soil. They would diffuse around and become fair game for photons, and we clearly do not see those. So that is telling me, at least that's my conclusion, that something grabs those new sodium atoms, and if it does, why doesn't it grab the old sodium atoms? So in that sense, I think there's some reactions going on. You have to lose them. Forget about the solar wind event. The same is true in the meteor
You're talking
shower.
about the solar wind. No, the meteor shower is colder. It's different.
The meteor shower.
If this was a meteor shower, I would agree with you. But if it's solar wind event,
I
it's
think
not.
this concept though provides an explanation of why do we lose the meteor enhancement within 4 days. This doesn't happen with photoionization lifetimes. We don't lose it to space. I've done these models. It would take essentially a month. And the reason is the following. Every hop is 20 minutes, and then the particle stays put for the next photon for a couple days, as I said, for any reasonable cross-section. So to accumulate 10 hours in air, it would take a long while. Instead, we lose it in 4 days, and it has to be to the subsoil, I believe.
Well, you guys, yeah,
we can
should
talk later.
Because I don't, yeah, interesting. Any other question? Very good. Thanks, Menelaos.